I began this project by reading the articles. After reading the articles, what really stood out to me is how the researchers analyzed 10 years of traffic data in the Twin Cities to understand how traffic changes over time and how the introduction of the light rail system affected driving patterns. They used data from hundreds of traffic count stations and looked at the trends by year, month, day of the week, and even by hour. One of the big takeaways that traffic generally increased over the decade, but the growth slowed down after 2004, which is when the Hawath light rail line opened. That timing suggests the light rail may have helped reduce some of the pressure on the highways. They also found really clear seasonal and weekly patterns. August consistently had the highest traffic, while January had the lowest, mostly because of winter weather and people leaving the area during the colder months. Friday had the most traffic, Sunday had the least, and weekdays made up the majority of the total volume. The daily patterns were extremely consistent, a morning peak around 7 a.m. and a stronger afternoon peak around 4 p.m., with the lowest traffic happening around 3 a.m. I began this project with exploratory data analysis, also called EDA. Exploratory data analysis was used to better understand the database, the data set before building prediction models. First, I imported the necessary Python libraries, including pandas, matplotlib, seaborn, and skit-learn. Pandas was used for handling and organizing the data. Matplotlib and Seaborn were used for creating visualizations, and scikit-learn was used for machine learning and regression modeling. After importing the libraries, I loaded the traffic dataset into Pandas data form. The dataset contained several columns, including year, month, hour, date, junction number, and vehicle count. I then inspected the dataset using functions such as head, info, and describe. These functions allowed me to examine the structure of the data, identify the number of rows and columns, check data types, and generate statistical summaries such as the mean, minimum, maximum, and standard deviation. I also checked the dataset for missing values to ensure data quality before building the prediction models. After understanding the data statistically, I created several visualizations to analyze traffic patterns visually. First, I generated histograms for the numerical variables. The histogram helped show the distribution of variables such as traffic volume and hour of the day. Next, I created pair plots and scattering plots using the most relevant columns, including hour, junction, and vehicles. Initially, the pair plots were very crowded because too many variables were included at once, so I simplified the visualizations by focusing only on important traffic-related variables. This made the graph easier to anticipate and help reveal relationships between variables more clearly. I also created a correlation heat map to examine the relationship between numerical variables. The heat map showed that an hour had some relations with traffic volume, although the correlation was extremely strong. During pre-processing, I removed unnecessary columns such as the ID column because it only acted as a unique identifier and did not contribute meaningful information to the traffic prediction. Removing unnecessary columns simplified the dataset and improved readability during analysis and modeling.
Alrighty, so for my portion of um, the project required us to separate models for each of the three junctions because behavior can vary significantly between locations. I separated the data set into three different data sets: Junction 1, Junction 2, and Junction 3. This allowed each model to learn traffic behavior patterns specific to its own junction. For each junction, I built two different regression models: linear regression and polynomial regression. Linear regression was the first model I tested. Linear regression attempted to model the relationship between the hour and traffic volume using a straight line relationship. For each junction, I selected hour as the input, which is right here, and traffic volume, oh wait, hour as the input and output as the variable, which is right here, vehicles. Um, the data was then split into training and testing sets using an 80-20 split. The training data was used to teach the model patterns in traffic behavior, while the testing data was used to evaluate how well the model performed on unseen data. After training the linear regression models, I generated predictions and evaluated the model performance using two evaluation metrics: mean squared error and R2 score. Mean square error measured the prediction errors, um, measures prediction error, so small values indicate better performance. R score measures how well the model explains the variation in traffic data, so values closer to 1 indicate stronger model accuracy. After testing linear regression, I created polynomial regression models for each junction, which is shown here. Polynomial regression is similar to the linear regression, but instead of using a straight line relationship, it allows a prediction curve to bend and capture nonlinear patterns in the data. This is important because the road traffic behavior changes throughout the day in curved patterns. For example, traffic volume may increase during morning rush and decrease midday, and rise again during the evening rush hour. I use polynomial features with degree 2 to allow the model to capture these curved relationships. After training the polynomial regression models, I again evaluated them using the mean squared error and the R2 score. Once all six models were completed, which is junction 2, the linear regression, and then the polynomial regression, junction 3, linear and polynomial here, I then compared their performance across all three junctions, which is shown here. Overall, polynomial regression slightly outperformed linear regression for each junction because it produced slightly lower mean squared error values and slightly higher R scores. However, the R scores remained relatively low overall. This indicated that our alone was not strong enough for the variable to fully explain the traffic behavior. Yes, that's my part.
After we compared the models and decided that polynomial regression performed slightly better overall, I decided to create a user input interface so the model could be used in a practical way. The interface asks the user to enter two pieces of information, the junction number and the hour of the day. The junction number tells the program which traffic zone or junction model to use. The hour tells the model what time to predict traffic volume. I used an if, elif, else structure to select the correct model. For example, if the user enters junction 1, the program uses the polynomial regression model trained for junction 1 data. If the user enters junction 2, it uses the junction 2 model. And if the user enters junction 3, it uses the junction 3 model. This is important because each junction has its own traffic behavior. A model trained on junction 1 should not be used to predict traffic for junction 2 because the traffic patterns may be different. Once the correct model is selected, the hour entered by the user is transformed using the same polynomial features process that was used during training. This step is necessary because the polynomial regression model was trained using transformed hour values, not just the original hour by itself. The model then predicts the expected number of vehicles and prints the result. This satisfies the project requirement interface for using the model. The next part of the project required using the model for each zone to determine projected traffic volume at specific times of the day, 2 a.m., 6 a.m., 3 p.m., and 7 p.m. To do this, I converted each time into 24-hour format. So 2 a.m. became hour 2, 6 a.m. became hour 6, 3 p.m. became hour 15, and 7 p.m. became hour 19. And for each junction, I used the trained polynomial regression model to predict traffic volume at those 4 times. I repeated this process separately for junction 1, junction 2, and junction 3. This gave me a table of predicted vehicle counts for each junction at each required time. These predictions represent estimated traffic volumes based on the patterns the model learned from the dataset. They are not exact values, but they show how the model expects traffic to behave at different times of the day. I also include an assessment of uncertainty because prediction models are never perfectly accurate. In this project, I assessed uncertainty using the model evaluation metrics mean squared error and R squared score. Mean squared error measures how predictions are values. A larger MSE means the model has more prediction error, while a smaller MSE means the model is more accurate. R squared score measures how much of the variation in traffic volume is explained by the model. In my results, the R squared scores were relatively low, which means the hour alone does not fully explain traffic volume. Because of this, the projected traffic volume should be interpreted as estimates rather than exact predictions. The uncertainty likely exists because traffic is affected by many factors that were not included in the model, such as weather, accidents, holidays, construction, road conditions, and special events. So even though the model can identify general traffic patterns by hour, there is still uncertainty in the predictions because real world traffic is more complex than just time of day.
Perfect. That is our project, top to bottom.